Frequency was how often something happens. What we did not discuss was the unit of frequency. Your unit of frequency is called a hertz. And again, just named after somebody's last name. We abbreviate it with a capital H and a lowercase z. You've probably seen that already in different places. And a hertz is the same thing as 1 divided by a second. And again, if you're not taking notes right now, and one reason why I have a screen on or a camera on everybody's face is I can tell within a certain reasonable amount of reasonable suspicion, I can tell who's taking notes and who's not.
Was it 1 over 5 or 1 over 7? I don't.
That's 1 over second. Good question, because 5s and S's look a lot alike, especially the way that I write them. So what this means is you're talking about how many times per second. So for example, if you see 60 hertz, that means 60 times per second. And 60 hertz, by the way, is the frequency of your alternating current in the United States electrical power grid. 60 hertz is going to be one that we're going to use quite a bit through the rest of the year. Your thing that looks like an upside down Y is your lambda. It represents wavelength. Your V will be velocity, your wave velocity, just like we're used to using V for velocity. And your A will be your amplitude. And then, of course, I'm watching your faces right now to get an indication for when you're finished copying your notes down. Your faces and Kira's forehead, because that's about all I can see on you, Kira. There we go. All right. Does anybody still need what's on the screen? Okay. All right, so there are going to be some of these features that we're not going to play with right now, but perhaps you saw that you could do square waves, you can do triangle waves, you can do longitudinal waves. We're going to focus on sine waves right now and transverse sine waves at that. I'm going to set it up for the first problem on the worksheet. I'm going to turn on my dots. I'm going to set it up for perfect destructive interference. And we're going to go ahead and put in some references so that we have kind of our XY coordinate axis and some other features here to help us see what's happening. Now, as I play my wave, I can see that I have my wave 1 and my wave 2. They show up. I can see very specifically what their patterns are. But, and you can tell me in the chat or by unmuting yourself, what's happening with the resultant wave right now? All right, Kira told me in the chat. Got a bunch of people waiting for the other person to say something so they don't have to say something. Annabelle told me in the chat. Even over Zoom, I've got some of you avoiding eye contact. What is happening to the last wave? Zach, I don't know what you would have to finish, because we're not doing this worksheet together, or we're not doing the worksheet exactly.
Yeah.
Sorry, not you, Zach. Zach E, it was Zach L. Alright, heard from Rebecca in the chat. Alright, everybody. I want you to do something for me. Oh, okay, Zach. Yeah, that's what... I get that. Everybody stand up. Wherever you are, home or school, stand up. All right, most of you can hear me because I still see about at least two of you still sitting. Everybody, wave your hands in the air like you just don't care. Everybody, go to your right. Stretch to your right. Stretch to your left. Go wiggle, 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 and go sit back down. Alright, from that exercise, I can tell you can hear me. I had to verify that for sure. And stretching can help us get our brain juices flowing. So, I will go ahead. There were several people that told me this in the chat. What we see here is we have perfectly destructive interference. And we see that our resultant wave disappears for all intents and purposes. Your resultant wave is not moving. What I would like for you to do, and you are welcome to, for if you're in the room, to say this to a neighbor. I would like you to make a prediction. Mathematically, how could we describe what's happening between wave 1 and wave 2 to get wave 3? If you are... Actually, let's go ahead and send you into breakout rooms. Let's do that instead, because there are some of you at home, and I do want you to have somebody to talk to, too. So, I want you to talk to whoever's in your room, and please, I do mean breakout rooms, in this instance. Please talk to whoever's in your breakout room about what is happening here. How mathematically are we putting together wave 1 and wave 2 to get wave 3? I'm going to give you about 90 seconds in your breakout room. On your mark, get set, go. Okay, just a couple people more to go. All right, Trey, tell me in your group, what was your prediction about mathematically what's happening here?
So like the lines where the wave is like going on, you take like the distance from like that one line and where the wave is for both of them, and you add them together.
And your distance, can you be a little more explicit? What do you mean by distance?
Oh, from like the line, you know, like those bars that are like on the graph that are going to like from the line and to the wave.
So like this bar that's over here?
Yeah.
Perfect.
That's
all
what
right.
I asked them. Okay.
Uh-huh. So remember that this line that's in the center here is called the rest position. So you're looking to see how far away you are from the rest position. Notice that here, if we look at this bar, this is above rest position. And here we have something below rest position. And Trey, what are we doing exactly with those bars? Go ahead and tell me that again.
We're like adding the distance, since like the blue one, it has like negative distance, and the orange one has like positive, and they just cancel each other out.
Perfect. So we've got a negative distance on the blue. We've got a positive distance on the red. And we're taking our red position plus our blue position, which when we add a negative number becomes the same thing as a subtraction, and we get our resultant position. And it just so happens that our red bar and our blue bar are the same heights, but one's positive, one's negative, so they cancel each other out beautifully. Now, Justin, you told me in the chat what this reminds you of. Would you go ahead and unmute yourself and tell everybody what it reminds you of?
Noise canceling headphones. It's the same principle of how they work.
So noise canceling headphones, true noise canceling headphones, to my knowledge at least, are a relatively new piece of technology. Meaning like really refined in the last decade or so. Before, if you wanted to cancel out noise, you just put something really heavy in front of your ears. Big old headphones that just blocked the noise. But what's different about noise canceling headphones? They're doing more than just blocking.
They're physically like destroying the sound. That's why it's called a destructive frequency.
Uh-huh.
Because they are taking whatever outside noise comes in and making a noise of equal pitch, I guess, and they are meeting at the same intervals, and that's why you hear nothing. But that is also why, no, they're out of phase. They're meeting at different intervals. And that is why when you put on noise canceling headphones and turn them on, there is a pressure on the head because it is out of phase.
Okay.
Like if you've ever been to Best Buy and tried them on, there's that pressure when they first turn on.
Yeah. I've never
and
actually
that is
worn them.
why.
So, yeah, so you're still getting a sound signal that's being sent to your ear, but it's able to read the sound signal coming into your ear in the first place and create a sound signal that matches that first one, but's flipped. or out of phase, as Justin said, in a way that they cancel each other out completely. And this is going to be kind of a little super basic. But it's super impressive they can do this because sound waves are much more complicated than what we're looking at on the screen. Sound waves maybe look something more like this, where even within a single word, I'm getting a variety of waves put together to create that word. A variety of frequencies, a variety of amplitudes are showing up. And so the fact that we've been able to develop this technology that can read those signals that are coming so fast and match them and flip them is absolutely fantastic. But that's probably the most practical use for destructive wave in the real world in a way that you might be aware of. So, which also, by the way, I forgot to tell this to my other classes, but 2 summers ago, I was able to go on tours at the Air Force, the Air Force headquarters in Dayton, Ohio. And they took us to a sound lab where they were studying this sort of thing exactly. Any guesses as to why the Air Force would be interested in noise cancellation?
Because they're like to pilots, like their planes or jets.
Their pilots definitely, but when they described it to us, there was actually another group of people they were even more concerned about than the pilots. But it did have to do with the planes.
Oh, was it to make radar? Well, no, radar's light based.
No,
No.
It wasn't radar. Radar is actually still sound based.
Okay.
Or it's electromagnetic frequency, so that is more light. Sonar is the sound based one. It was more about, it still was about protecting people. And so for what Zach said, the pilots definitely were a group that they were concerned about, but the people they were super concerned about were actually the people on the ground. Do any of you work at the airport by chance? Usually I have a few students a year who work up at our Salt Lake airport. Lily, what you said, it damages your ears, especially the people on the ground who are like the people waving the planes around. They're the ones who actually have the most sound damage to their ears and the ones that they're really worried about protecting. And for up until recently, and even now, I think that typically they have the sound blocking technology. In other words, it's a big headphone that all it does is block the noise. But they're really working at the Air Force headquarters to try to figure out cancellation, which then we get in anytime the military, not anytime, but oftentimes what they develop in military does trickle down to consumer goods as well. Dresden, you still with me? That they're trying to figure out better and better ways to create the noise canceling effect to protect the ears of the people who are working in guiding the planes around. All right, so let me pull back up the worksheet because, like I said, I'm using it as a guide today, and there's one more thing we are going to do with destructive interference. Okay. Do you see this wave? Let's do one like that. You see the wave on the screen right now? Wave A or wave 1? Would you please copy this wave into your notes? And then over top of it, would you please copy the wave that would completely destruct wave 1 if we were to add them together? On your mark, get set, go. And when you finish creating your perfectly constructive or destructive wave, would you please have a staring contest with somebody on the screen? Which means, Zach Lloyd, I'll need to be able to see your face and not the ceiling. There we go. Okay, and Aaron, you'll need to make sure your face is in the screen if you're having a staring contest, just so I can see that. Alright, so you should have something that looks something like this on your paper. Emily, I don't know what you mean by that. Alright, we should see two waves that completely, perfectly are out of phase from one another. Our crests on the red wave line up to the troughs on the blue, and the troughs on the blue wave line up to the crests on the troughs on the red wave line up to our crests on the blue. Alright, now, do you have a prediction for me, please? I'm going to talk next about constructive interference. Do you have any predictions about what two waves that are constructively interfering will make, what we'll do? What will our resultant wave look like? Go ahead and write on your paper. You don't need to tell me, but I just want you to make a prediction. When we have constructive interference, what do you think our resultant wave will look like? Write it on your paper. We'll see in a moment if you're right. Destructive makes your resultant go away. What will constructive interference do? Justin, we will actually come back and talk about that at the end of class. So save what your example is, and we'll do that with the example I have as well. All right, 10 more seconds to write down your prediction about constructive interference. Is this what you predicted? Meaning the purple line down at the bottom. Or does it look similar to what you predicted? Isaiah, you still with me? Okay. Give me a thumbs up if it's related to what you predicted. Give me a thumbs down if it's not. I don't care if you have a thumbs up or thumbs down. I can't see what's on your paper. I'm just curious. Okay, Lily, Kira, I can't see your thumbs. Emily, you'll have to show me with the features on Zoom. Aaron, I can't see yours. Okay, still missing some thumbs, but we'll go with it. All right. So, could you please tell me, what do you see happening here? When I take wave 1 plus wave 2, how is it related to wave 3 mathematically? I'm going to send you back into your breakout rooms to discuss very, very quickly. And then I want you to come back and tell me mathematically, how do we go from wave 1 and wave 2 to the resultant wave? Your breakout rooms are open. Okay, just one more person we're waiting on. All right, McKinnon, in your group, could you tell me what was your prediction about how we go from 1 to 2, or 1 and 2 to 3 mathematically?
They're we thought that they were both the same, so that they add up and they like double each other, I guess. Like the previous one, they cancel each other out, and this one is they're like doing the opposite of canceling each other out, I guess.
So, but the key thing I heard is you're still saying you're taking the height of a particle from wave 1 plus the height of a particle from wave 2 to get wave 3. And let's check that out. So, for example, I'm going to try this represented here. We have our height of a particle from the red wave at the same position. This is where I had some difficulty last class too. We have our height of our wave from our second. Lily, I'll get into that in a second. And are those the same height? So here we have this one was from wave 1, this one was from wave 2, and this one was from wave 1 plus 2. Are they the same height as each other? If I take the height of 1 plus the height of 2, do I get the height of 3? All right, Kyle can hear me. And he might be the only one. Everybody, clap 3 times. Okay, good. More of you can hear me. So tell me, mathematically speaking, using my visual representation, if I add these two together, does it look like I get the height of the third thing? Okay, good. That's 5 more of you can hear me. Okay. I know the internet might be have issues, but if I say things like clap and you respond, I can see you can hear me. And all I'm looking for is a yes or a no. All right, so what we found in each case is when 2 or more waves interact, you add together the heights of corresponding particles to find the new resultant wave. Whether it is constructive or destructive, it is the same. It just so happens when it's destructive, one's up, one's down, they cancel. When it's constructive, they're in the same direction. And they just amplify or make bigger the wave that we're looking at. Isaiah and Lorian, I'm looking at your eyes. If you're copying this down into your notes, you're perfect. You're golden. From your eyes, it's hard to tell if that's really what you're doing. Perfect, Isaiah. Thank you. And Lily, again, I will come back to your question, but not quite yet. All right, I'm going to mix this up a little bit now. We'll leave the notes at the bottom if you're still copying those. But I'm going to play with my first two original waves. Notice that each individual first wave is still a nice, smooth, just what we had before wave. But these are waves that are out of phase from one another. They have different frequencies. And I am going to be taking, for any individual particle, I'm going to be taking the height of the particle at that point, add them together, and I'll get the height of the resultant wave. What do we see here in our resultant wave when we do that? Is it as predictable as the last two were that we looked at? Got a response from Annabelle, from Kira. And again, all I'm looking for is a yes or a no. Or a thumbs up, thumbs down, Lorian. Yeah, that was perfect. Getting different responses from different people, and honestly, the question I asked you was subjective. We don't get a regular amplitude out of our object, but visually maybe you prefer this sort of wave. Now, yeah, let me do my examples and then I'll go through the questions that people have been sending me in the chat. Let's talk sound for a moment. Now, there are multiple types of waves. Sound waves are one of them. And sound waves are things that we will study more in depth later. In fact, later I will be pulling up these frequency generators and we'll be testing your hearing. So, as I go about this, let me say, first of all, I'm going to leave it on you to adjust your own speakers. We are doing sound. It is possible to hurt your ears. So, if it starts to hurt your ears, please do just turn your sound down. And in fact, you might want to start with your sound a little bit lower. Please, loud enough so you can still hear me. But you might want to turn down your sound now and then turn it back up to be able to hear our tones in a moment. So, let's start this off. I have two frequency generators. By the way, have you heard of tuning forks? Do you know what a tuning fork is? Each tuning fork can only play one frequency. This is the online version of a tuning fork. Alright, so I'm going to play this. I want you to give me a thumbs up. I'm going to go ahead and maximize on my speakers so you minimize on yours. And again, these can't hurt your ears, so please do adjust your own speakers so it's not painful for you. But give me a thumbs up if you can hear this, a thumbs down if you cannot. Okay, saw from everybody. Krista, I couldn't see you at first. And Emily, I didn't get a thumbs up from you. But tell me now if you can hear. I'm going to adjust this one to probably right about here. Tell me if you can hear this one. Jake, I didn't see a thumb from you or from Emily. Alright. Aaron and Jake, go ahead and adjust your speakers and make it as loud as you can if you need to. And then tell me, if you still can't, let me know. And Emily, I need some feedback from you. I need to know you're still there. So with each of these tones, they're each playing one note. And in fact, if you're somebody who's musical, we have the note right there. They tell us which note we're using. Approximately, we've got an E2 and an A2. So as I play these, we had these two even tones that they each had their own frequency, their own wave that was just ideal wave like what we just saw. Very even. Now let's see what happens when I play them together. Does that sound like a wave that's even the whole time, playing one note as you go? What does it sound like? Find your own words to describe. What was that like when I played them together?
Felt like they were playing ping pong with my body.
Ping pong. In the chat I'm seeing bumpy. It felt bumpy. Like there's different ways we can use to describe this. Lorian's kind of going like this with his fingers, kind of up and down. Like they're running into each other. Justin says unpleasant. To me it reminds me of a helicopter or something like this. It was awful. It felt like sounded like sound flashing. All right. So what's happening mathematically here is something like this. Oh, there we go, Emily. Just wanted to see if you were still there. So what's happening here is we have these two, I'm going to call them consistent frequencies. Here and here, both consistent frequencies. Let's kind of curve that though. And what happens here when we get an inconsistent, and it's still there's still a consistency to it, but it's a different sort of consistency, I should say. We hear these points that have higher amplitudes. And higher amplitudes will sound louder. And then we have these places of lower amplitudes, here and here, and they will sound quieter. And so we're going to get this loud, soft, loud, soft, loud, soft, loud, soft, loud, soft. But it was happening much faster than that with the frequencies that I chose. What's happening here, whenever you have this happening, you get something called beats. When you have beats occur, they're going to be two frequencies meet and they're out of phase from one another. And you get that pulsating noise in your ear. Something we're going to talk about more when we talk about sound in particular, but this is just to bring together the visual and the audio to explain what it is we're seeing. Okay, so I want to answer Lily's question first, and then Justin, you had some things about examples of out-of-phase waves. I'll do that next. So in the chat, Lily asked me, doesn't it depend on the surface it reflects off of, like if it's solid or moving? And so, yes, it does. We're going to talk in our next class about reflecting waves. Right now, we're not reflecting waves. We're sending waves together to your ear, and so there's no reflection except for off one. I guess in the room, it's maybe reflecting off the bookcase or the walls or things behind you. But really what we're doing right now is we're sending them to you without any reflection. But next week we are going to talk about how when you reflect a wave back, or not next week, it'd actually be Thursday. When you reflect a wave back, it can produce a wave that's out of phase, or it can produce a wave that's in phase. And it's not so much about the material Although the material it depends on the material, it depends on what wave I send at it in the first place. We're not going to go crazy in depth on the different surfaces, but it will play a part. Which is why, for example, if you decide to listen to loud music or a concert inside a room that doesn't have any soundproofing, chances are that music will sound terrible to your ear. Based on your question, Lily, that those sounds will reflect off your surfaces in a way that will be unpleasant to your ear. If you go into a concert hall, you will see soundproofing on the walls because they want the only sound to be the sound that comes straight at you. They don't want to also have the sound that's coming off the wall, that's bouncing off the wall and hitting your ear. They don't want those to come together because together they do sound terrible. Aaron. Yes, now would be an appropriate time for that. Make sure you use the hall pass. All right, Justin, you said that you had an interesting example. Could you share that example with us?
Sure. It's a little bit obscure, but it's Peter Green. So there were two different lineup changes for the band Fleetwood Mac. There was the original guitarist, Peter Green, and that is who we're talking about, and then Lindsey Buckingham. His guitar was unique because it was wired wrong from the factory, and instead of the electromagnetic pickups being wired in phase, in series, as they would normally be, it was wired out of phase.
Uh-huh.
Thus creating, when you had both pickups running simultaneously, it created this really interesting kind of whiny, high-pitched sound. Best shown on the song "Oh Well," which was one of the last songs they did with Peter Green.
Okay, and I'm looking up Peter Green out of phase. Interesting. This is an example I've never heard. Let's clear all this. So, I don't know if you're familiar with any of these, but I'm just going to guess that this maybe would be a good video.
Hey guys, got a quick lesson today on the Peter Green.
Not specifically on. That's how he
what it is
played,
and how
like
to use
physically
it.
played the strings.
Uh-huh.
What that is, what I'm referring to, is see those silver boxes on the guitar itself?
So, silver boxes?
They're called pickups.
Yeah, my guess is these are people who are explaining that.
Yeah.
Which, let's get to a point where it looks like he's playing.
Okay, let's just try another song so you can kind of get the flavour of this pickup.
That kind of gets the sound.
Okay. No, that's really interesting, and that makes sense that if they switch the electromagnet on accident. Right now, you can hear my voice, and I think we talked about this before. Kyle, put whatever you got away. Right now, you can hear my voice. It's not that the sound waves from me are hitting you, but we're using electromagnetic ideas for my voice is being converted into an electromagnetic wave, goes through the internet. That wave itself, that waveform is then reinterpreted as sound for your speakers. And that wave then is being sent out, converted from electromagnetic back into sound. And there are ways that if you mess with the electrical current of what is happening, it will distort my sound so that I would come out sounding different. It makes sense. I can imagine, I don't know, but I can imagine that after this one guitar in a famous band was created in an incorrect way, I would imagine that a lot of artists would probably take that and would use it to play with to create new sounds that we weren't necessarily accustomed to.
Several did. Gibson, which is the maker of the guitar, and he is holding a guitar called the Les Paul. They ran. He gave his guitar back to him because he bought it in, I want to say it was 1959. It was a 1959 Sunburst Les Paul. That was, all those guitars back then were handmade. That was the first solid body electric guitar. All those guitars were handmade, and they had just messed it up completely, and while wiring it. And so Gibson, so 20 years later, when Fleetwood Mac gets big and you have hits like Oh Well, Gibson is like, what is up with that guitar? Sends it back to him, and they find out, oh, the pickups were wired almost completely backwards.
Which, I mean, it would be pretty easy to do, and I've never wired an electromagnetic magnet, but it really, to my knowledge, would be as easy as just switching your wires.
It basically turning them, the way you like wire a pickup is you wrap a bunch of copper coils around a magnet.
Yep.
And you have poles to conduct the electricity. The way that you would do it is if you just happen to, if the machine is supposed to go spin one way, they might have just accidentally hit it and it would have spin the other way.
Yeah, and that would be very similar if you switch the wires. That spinning them the wrong way would change the direction of your magnet. Something that we're not really going to go into depth in this class on that, but we'll touch on it later, right before the end of the year. All right, let's see where we're at. We are going to have some time. Perfect, because we've gone through what I wanted to go through here. Did I talk yet about square waves and triangle waves? I don't think I did that for your class yet, did I? All right, let's talk about those for just a moment. While we're not going to really touch on them in this class, there will be times where in other locations you might change the way your wave is formed. It's literally called a waveform. So, how many of you have ever learned about binary systems? Okay. It's something that back when I was in school, we never really seemed to touch on it, but you guys have. So, when I talk about binary, what is binary and where do you usually see it? And Kyle, stay with me. What is binary? How do we represent binary? All right, Annabelle told me in the chat. It's a bunch of ones and zeros. Ones and, not ands. And you're going to see it typically in computer science. It is a mathematical idea, but it's applied in computer science. So that's the place you'd be most likely to see it. And when we talk about binary, it's ones and zeros, which typically represent on and off. Your light switches, for example, are binary even if it's not a computer. You only have two choices. Binary means you have two choices and only two. With binary systems, we can represent those ones and zeros with a waveform, and so you could send this electromagnetic waveform into a computer system, and it would be able to read on versus off. Your highs would be ons, your lows would be offs. And we could send this sort of frequency of our own creation into the wave and use that ultimately to create computer programs. There will be places in physics where you're going to use square forms, just not at this level. I'm not going to focus on the different types of waves, but since this interactive brought them up, I thought it'd be worth showing you. But mathematically, they're going to work the same as the other waves. We're still going to represent the amplitudes and such using the same ideas. Another waveform that you can do is a triangle waveform. And again, there's just different purposes for when you'd want to see this. Triangle waveforms, you're more likely, so let's see, this was the square, is like your binary. Your triangle waveforms, I can tell you, I use them mostly with representing AC current, which is kind of redundant because the C in AC already stands for current. What does AC stand for? What does the A represent?
Alternating current.
Alternating. And literally what it means is you've got an electron, you send it one way, and then you reverse the direction. And you keep vibrating it back and forth. Out of curiosity, do you know how many times electrons vibrate back and forth in the United States alternating current that is standard across all circuits?
60 hertz.
60 hertz. So in the US, you use 60 hertz circuits, and we can represent maybe this high point would be going to the left, and the low point maybe is going to the right. And we're just worried about, as you change direction, that moment you change direction, which direction are you going? And again, these ideas, when you talk about your waves, all three of these are going to really be using the same ideas of frequency, wavelength, amplitude, etc. But we have different reasons for why we like the different wavelengths once you get further in physics than we are now. And in this class, where are my sophomores at? Okay, sophomores, you should not have seen this yet. If you're in Math 2 honors, maybe you have, but even then I don't think you've gotten to this yet. Juniors, where are my juniors at? Juniors, depending on the math class you're in, you may have seen this. Even the Math 3 regular, if you haven't learned this yet, you should be learning it soon. And seniors, I know you've learned this because I taught it to you for many of you. But the one I did not talk about, the one that we're most accustomed to, is the sine wave, just as a heads up to your math class. For my sophomores and my juniors, literally when you graph the function sine of x that you learned about in your freshman and sophomore years of high school, the function you get out, the wave that you get out, looks like the wave that we're using in this class. So that is why it's called a sine wave. I did have people in my other classes ask me about using cosine waves, which look identical to sine waves. They're just out of phase from each other. Because they're so similar, we don't bother to say both. We're just going to refer to all waves of this shape as sine waves in this class. All right. So, to go back to today, we did not do the worksheet exactly. What I want you to do for points today, let's wait for it to finish loading. Okay, what we just did was 31.1a. All you need to do is take a picture of your notes from today, and that's what I'm going to count as your credit. This is due today. So you can get this done right now if you got a phone. I can see Lily's already doing it. That's perfect. Your discussion question is also due today. So after or before, depending on if you have a phone with you or not, which I know you guys, most of you do, please go ahead and do the discussion question for today. And then your assignment and your quiz are both due next class.